Have you ever wondered how it all started, this vast universe we live in? Today we'll delve into the birth of it all, the cosmic origins of everything, the Big Bang Theory. Imagine, if you will, a time around 13.8 billion years ago. Picture all the matter and energy in the universe condensed into one singular point. It's hard to fathom, isn't it? But that's the magic of the cosmos. Its sheer scale, both large and small, always leaves us in awe. This singular point, this seed of the universe, was a place of unfathomable density and infinite heat, a place where the laws of physics as we know them today did not apply. It was a realm of pure potential, a cosmic singularity, a place outside of time. Then, in an event known as the Big Bang, this point exploded, but it wasn't an explosion like any we know on Earth. This was an explosion of space and time itself. It was the birth of the universe. From this singularity, the universe began to expand at an incredible rate, a rate that continues to this day. The explosion didn't just scatter matter and energy into the void, it created the void, it created space and time. It was the beginning of everything. From this single point, the universe expanded and cooled. Matter and energy spread out, forming the cosmic structures we see today. The galaxies, stars and planets, everything we can observe and everything we cannot, were all born from this singular event. So the next time you gaze up at the night sky, remember that those twinkling stars, those distant galaxies, and even the darkness between them, all came from that one point, that one moment of creation billions of years ago, a moment that set the stage for everything that has happened since. From that single point, everything we know and everything we don't sprang into existence. As the universe expanded, it cooled and matter began to form. In the beginning, the universe was a hot, dense soup of particles. But as it expanded, it cooled. After about 380,000 years, temperatures had dropped enough for protons and electrons to combine and form the first atoms, mostly hydrogen and helium. This period, often referred to as the era of recombination, marked the birth of matter as we know it. But the universe was not yet the star-studded canvas we see today. For that, gravity had to step in. Gravity, ever the cosmic sculptor, began to pull this primordial matter together. The denser regions attracted more matter, and these clumps grew larger and larger. Over time, these clumps evolved into vast structures. The galaxies, each galaxy, a whirl of billions of stars, bound together by the force of gravity. Speaking of stars, the first ones began to form within these galaxies about 100 million years after the Big Bang. These stars were much larger and hotter than our Sun, burning brightly and living fast. They were the universe's first luminaries, casting light into the cosmic dark ages. But these stars had another crucial role to play. You see, the only elements in the early universe were hydrogen, helium, and a smidgen of lithium. Everything else we know, carbon, oxygen, iron, the elements that make up our world and our bodies, didn't exist yet. These heavier elements were cooked up in the hearts of these first stars. Through nuclear fusion, stars fused lighter elements into heavier ones. And when these stars reached the end of their lives, they didn't go quietly. They exploded in spectacular supernovae, spewing their enriched guts across the cosmos. This stardust, enriched with heavier elements, would then become the raw material for new stars, new planets, and eventually life itself. In the fiery hearts of these first stars, the building blocks of life were created. Scene script. About 4.6 billion years ago, in a galaxy we now call the Milky Way, our solar system was born. Our story begins with a massive rotating cloud of gas and dust known as a nebula. This nebula, rich with elements forged in the heart of long-dead stars, was the cradle of our solar system. As gravity tugged and pulled at the nebula, it began to collapse under its own weight, forming a spinning disk with a hot, dense center. In the heart of this swirling maelstrom, the core of the nebula heated and compressed until it sparked the birth of our Sun. The fusion of hydrogen atoms into helium released a tremendous amount of energy, causing the Sun to shine brightly. This powerful process, known as nuclear fusion, is what gives the Sun and all stars their light and heat. But what of the planets, you might wonder? Well, as the Sun blazed into life, it left behind a disk of gas and dust. Within this protoplanetary disk, tiny particles began to collide and stick together, forming planetesimals. Over millions of years, these planetesimals gathered more and more material, growing into the planets we know today. Our Earth, Mars, Venus, and Mercury formed close to the Sun, where it was too hot for ices to survive. These terrestrial or rocky planets were born from the dust and metals in the protoplanetary disk. Further out, where it was cooler, the gas giants Jupiter and Saturn began to form, their massive sizes allowing them to hold on to the lighter gases. Even further out in the frigid depths of the outer solar system, the ice giants Uranus and Neptune took shape. These distant worlds captured heavier ices such as water, ammonia, and methane, giving them their characteristic blue-green hues. And let's not forget the countless asteroids, comets, and dwarf planets, each a relic of our solar system's violent birth, each with its own unique story to tell. From the dust of a dying star, our home was born. On a small blue planet, third from its sun, life began to emerge. Our tale now turns to Earth, a cosmic oasis where conditions were just right for the miracle of life to occur. The exact mechanisms of how life first sparked into existence remain shrouded in mystery. Yet scientists have pieced together a fascinating tapestry of theories, each more intriguing than the last. One such theory suggests life began in the depths of the ocean in hydrothermal vents. These underwater chimneys spew out hot, mineral-rich water, providing an environment that could have nurtured the first life forms. Picture, if you will, the first self-replicating molecules swirling in the warm and mineral-rich broth of these deep-sea vents, gradually evolving over millions of years into the first simple organisms. Alternatively, some propose that life was delivered from the stars themselves, hitching a ride on comets or meteorites. This panspermia theory posits that the seeds of life may be common throughout the universe, sown across the cosmos by these cosmic wanderers. But no matter which theory holds true, what happened next is nothing short of miraculous. These simple organisms began to evolve, diversifying into a multitude of forms. Over billions of years, through a process of natural selection and mutation, these simple life forms became increasingly complex, branching out into the awe-inspiring diversity of life we see today. From the tiniest microorganisms to the largest whales, from plants silently reaching for the sun to birds soaring high in the sky, life has adapted and thrived in every conceivable environment. It's a testament to the tenacity and adaptability of life, a story written in the DNA of every living creature on Earth. This blue planet of ours, adrift in the vast cosmic sea, is home to an incredible array of life, each form intricately connected in the web of existence. From the depths of the oceans to the highest mountains, life has found a way. What does the future hold for our universe? A question that has intrigued humankind for centuries. As we peer into the cosmos, we are peering into the potential future of our universe. There are several theories that astronomers and physicists have proposed about the ultimate fate of our universe. Two of the most popular theories are the Big Crunch and the Big Freeze. Let's delve a little deeper into these fascinating concepts. The Big Crunch theory suggests that the universe, which is currently expanding, may one day start to contract. This could happen if the gravitational pull of all the matter in the universe overcomes the force of its expansion. In this scenario, galaxies would start to merge, stars would collide, and eventually, all matter would collapse into a singularity, a point of infinite density. That's a bit like running the Big Bang in reverse. On the other hand, we have the Big Freeze theory. This theory is based on the observation that the universe is not just expanding, but its expansion is also accelerating. If this continues, the universe will keep getting larger and colder. Eventually, stars will burn out, galaxies will drift apart, and all matter will decay, leaving a dark, empty universe. While these theories might seem unsettling, they're part of our quest to understand our place in the universe. By studying the cosmos, we gain insights into the laws of physics, the nature of matter, and the origins of life itself. So, what does the future hold for our universe? The truth is, we don't know for sure. But with every new discovery, we're getting closer to understanding the cosmic narrative that we're part of. As we gaze into the cosmos, we're not just looking at the stars, but also into our past and possibly our future. We are, after all, made of stardust, and to the stars we shall one day return. In the grand scheme of things, we're not just observers of the universe, we're participants in its unfolding story.